analysis first. Okay, that's the first thing I'll get worried. Okay, they give me NN, and they did not tell me that distance. Okay, so is that distance important or not? Okay, so for this case, later on I'll show you it seems not important. Other cases, it might seem to be what? Critical. So always what? Check. Okay, so now I'm going to draw our free body diagram. So this is X, Y, rotation about Z. Okay, so we have a diagram doing this. So this is our point A, and this is our point B, and directly at the center is a load of 180 times 10 to the power 3 Newton, and we know that the distance from here to here is 0.5 meters, and also from here to here is 0.5 meters. Okay, so this is your AY, and this is your BY. Okay, so we can perform static analysis. Okay, so summation of moment in the Z direction. Okay, and we're going to take moment from point A is equal to 0. So this will be equal to minus 180 times 10 to the power 3 multiplied by 0.5, right? Then plus by BY multiplied by 1 meter. The whole thing equals 0. So BY is equal to 90 times 10 to the power 3 Newton. Okay, and then you do summation of forces in the Y direction is equal to 0. Going up is positive, so AY minus by 180 times 10 to the power 3 plus by BY, which is 90 times 10 to the power 3 is equal to 0. So AY is also 90 times 10 to the power 3. Or, okay, or or another way to solve this is based on symmetrical geometry and loading condition about the y-axis. So the y-axis over here refer to where the load is applied to the y-axis. Okay, you can say that AY now has to be symmetry in terms of geometry and loading. So left and right, you see the 0.5, right? And at the exact position, you have AY and BY. Okay, so when there's a case, AY is equal to BY. Okay, and all you need to do is positive is going up. Summation about forces in the Y direction is equal to 0. You can write AY minus 180 times 10 to the power 3 plus by BY is equal to 0. The fact that AY is equal to BY, you replace this by AY, so 2AY is equal to 180 times 10 to the power 3. Okay, AY is equal to 90 times 10 to the power 3, and this is equal to, sorry, AY is equal to 90 times 10 to the power 3, and this is equal to BY. Okay, but if you don't know based on geometry, it's okay. Do like what how I start, take your moment. Okay, it's okay, right? The answer will still be the same. Don't kill yourself. Okay, so next we are going to draw our shear force diagram. So where we are now in our solution is we have calculated our reaction at AB. Okay. Now we are going to draw our shear force diagram. Okay. Draw our shear force diagram. Okay. So our shear force diagram. Okay. So this is V. This is X. Over here is 0. Over here is 0.5. We have 1. At this line down here, this is plus 90 times 10 to the power 3 Newton. Down here is minus 90 times 10 to the power 3. Okay. So over here, this is our point A. And over the other end, this is our point B. Right? So A has a reaction of 90. So it goes 90 horizontally. Then at the load where 150 at 0.5, 180 has been applied. So it will go down by 180. Okay, 180, right? And then it runs horizontally. And then it goes back up. And it goes back up. So this is positive now. So now, this is your shear force. Yeah, my distance is a bit off. Okay, my bad. Okay. So now, they ask us to find at NN down here. And this distance we don't know. X we don't know. What I'm going to ask you is this. Does it matter if you know where is X or don't know where is X? The answer is it does not matter, is it? Okay, because it's constant. So therefore, we have found that Vy is equal to 90 times 10 to the power 3 Newton. Okay, so that's where this question, they did not even tell you the distance. They did not bother. They just say, hey, find NN. Okay, we realize that, hey, yeah, I can find NN. I can find the shearing force at NN. Does not matter whether I know X, because from 0 to 0.5, it is what? 90, positive 90. So now I want you to watch the distance. The drop over here is what? Minus 180 times 10 to the power 3, right? And this is because the applied load, if you look at this question, we have an applied load of what? 180. Okay? Right. So where are we now in our solution procedure? Okay? We are now here. Okay? So now we are going to determine our shearing stress. But first, where we are now, we have to calculate the centroid position. Okay, so I'm going to teach you. I'm going to do a procedure. Okay, and I've done this procedure a lot of times. Okay, and I never make mistake. And from this procedure, I also create a marking scheme. Okay, I mean I create a Excel spreadsheet marking scheme that never make mistake. So all the good stuff I share with you. Okay, how to make sure that your analysis will always be accurate. So the next thing, we're going to find centroid. Okay, so I'm going to take a diagram again. I got another diagram. Okay, I want to find the centroid. Okay, so I'm going to divide this into 3 sections. Okay, so this is finding centroid. Okay, I'm going to so I'm going to divide this in such a way that this is 1, this is 2, and wait, I think I need this diagram to be big so you can see better. Okay, I think this is marvelous. This is 1, This is 2, and this is 3. Okay. Then I'm going to create a table. I'm going to create a table. Yeah, I'm going to create a table. So this table I call section. Okay. 1, 2, and 3. Okay, that's my section. Now, what we want to determine is where is our ZZ axis, right? So we want to find IZZ, right? So it's relative to the ZZ axis. So relative to the ZZ axis, this will always be our width, right? And then this distance, this geometry in this orientation will always be our depth, because we want to find what is on our IZZ, right? So I want to find the ZZ. I want to find big Y bar, not small Y bar. Okay, capital Y bar. Okay, what is that distance from the top? So from this case, the analysis to find the centroid. Okay, we are not finding shear stress. We're finding centroid. This is where the datum is. I'll take the datum from the top. Okay, so I declare datum from the top. Okay, then I will create a table. This table follow this format. Okay, don't follow what the solution manual says. Okay, only check where the key points are, key values, like what I demonstrated last week. Okay, so this is the width and this is the depth, because the solution manual did not do this. Okay, so for the section 1, the width is 160, the depth is 20. For section 2, the width is 20, the depth is 80. For section 3 and section 2, they are the same. So this will be equal to 160, 3200, 20 times 80, 1600. And then the next one is your Y bar. So small Y bar, I'll write down here. Small Y bar is the individual centroid or individual section centroid relative to the datum. So this will be 20 divided by 2. Right? Why? Because the datum's at the top for section 1, right, is down here. This is the individual centroid, which I've drawn and highlight, right, in yellow. That's the individual centroid. So the distance from here to here is 20 divided by 2. Okay. For section 2, it's equal to 20 plus by 80 divided by 2. Okay, so 20 plus by 80 divided by 2 is equal to 60. So why is it 60? Okay, so section 2 is only this section, right? So you divide by 2. This is 80 divided by 2, right? And the distance from here to here is what? 20. Okay, so likewise for the next part is the same. Okay, And the final one, oh, I'm so tight for space. I think I see whether can I squeeze the thing. Yeah, squeeze.